All right, in this video, we are going to look over our first test. All right, so first questions are all about intermolecular strength. So here we have a carbon bound to an oxygen. That's a polar bond. There's no hydrogen bonds. Remember, hydrogens is to F, O, or N. I don't see that. So since it's just polar, that's dipole-dipole. The next one, I do have an OH. So that tells me I have hydrogen bonds. So that would be the strongest there, hydrogen bonds. All right, so next one, I just have carbon, hydrogen, no oxygens, no polar, so that's just dispersion. All right, if I have a solution of water with sodium, so Na plus is an ion, water is polar, so that's an ion plus a polar, that's called an ion dipole. Which of these have the strongest intermolecular force? Remember, the higher the boiling point, the higher the molecular force. So that would be B. Which of these statements is true? As the strength of intermolecular forces increase, viscosity decreases. That's false. The viscosity gets stronger. The heat of vaporization becomes more positive. That is true. It becomes a bigger number. Right? Heat of vaporization is delta H VAP. So the stronger my intermolecular forces, the more energy I need to vaporize it. So delta H VAP becomes a bigger number. Right, let's go on to question 7. The process of going from a solid to a liquid is, we call that fusion. Is evaporization endothermic or exothermic? So when I'm going from a liquid to a gas, I have to put energy in to do that, just like boiling water on the stove. I have to do energy. If I'm putting energy in, it's endothermic for going in. So we already know that. And delta H is positive for evaporization, because that means I'm putting energy in, right? We are increasing our heat. It's going into the system. So that would be D. All right, moving on. Number 9 here. Why does water have a concave meniscus when it's in a narrow tube? All right, so we have adhesive forces. That's the water to the tube. And we also have cohesive forces. That's the water interacting with itself. So since the water is climbing higher in the tube than it is interacting with itself, you have stronger adhesive forces than cohesive forces. How would I find the heat of sublimation? Sublimation is solid going to a gas, right? That's basically what dry ice does. Remember, if I'm looking for the heat, anytime you see the heat of, that is delta H, and delta H's are additive. So the heat of going from a solid, liquid, then to gas is equal to going from solid to a gas directly. So going from a solid to a liquid, that was fusion. Going from a liquid to gas, that was vaporization. So I'm looking for adding the heats of fusion and vaporization. That is E. All right, in this phase diagram of Y below, what statements are true? So first off, let's refill out our phase diagram. We have gas down here. We have liquid right here. And we have solid over here. So at 0 and 1020, so 0, 1020, Y exists as a solid. No, we just said that's liquid, so it can't be that. As the pressure and temperature of 0.1, so here's 0.1, solid will spontaneously convert to gas and no liquid's possible. Well, you see all three lines are converging here. Remember, this is what we call the triple point. This is where you have solid, liquid, and gas at the same time. So liquid is possible, so it can't be that. Point 4. At the temperature and pressure at point 4, gas will spontaneously convert to liquid. Well, point 4 is in the liquid region. So if we have any gas at point 4, it has to be a liquid instead, so it will convert. So your answer there is C. Okay, which of these classifications is false? Sulfur solid is an atomic metal? No, sulfur is not. Oops, I should have circled that one. Sulfur is not a metal. Sulfur is a non-metal, so that is the false one already. So that one's A. All right, 13. I am making a solution from a polar solvent and polar solute. If delta H solvent's 32, delta H solute is 12, and delta H mix is 25, which is the following is true. So our equation here is when we are making the heat of the solution, we can figure out how much heat is absorbed or released from the solution. When we think about how much heat I need to separate the solvent, plus how much heat I need to separate the solute molecules from each other. I'll get it eventually. And how much energy is released when I mix them. So solvent is 32, solute is 12, mix is minus 25. That is some positive number, right? So since it's a positive number, this reaction is exothermic. No. Exothermic would be a negative value, so it can't be exothermic. When mixing, this would feel warm to the touch. No, that's what exothermic means. These would be immiscible in each other. That means they can't mix. No. Since delta H mix is a number, that means they are mixing. So they're not immiscible. This reaction would be endothermic. Yeah. All right. If it's not exothermic, it has to be endothermic. So based on this information alone, the only thing you can really say is this is endothermic. All right, moving on. 14. If I was to solve 40 grams, okay, so 40 grams of KCl, so KCl is my blue, and 100 grams of water, that's what this actually says, grams of solute and 100 grams of water. At 30 C, I would have so I'm looking at 40 to interact with 30. That's this point right here. I am above the KCl line. Remember, this line tells me my solubility. Since I'm above, that's called supersaturated solution. All right, 15. If I was able to dissolve 0.250 molar of O2 into water at 25 C, and the Henry's law constant for O2 at that temperature is 1.3 times 10 to the minus 3 molar per atmosphere, what's the pressure? So this is a Henry law problem. The solubility of gas is equal to our Henry law's constant multiplied by the pressure of that gas. So the solubility is 0.250. The Henry's law constant is 1.3 times 10 to the minus 3 molar divided by atmosphere. This is molar. So I want to multiply that by P. So I'm trying to find P. So I just divide each side by Henry law constant. I believe the answer is 192 because it has to be high. Yep, it is 192. All right, moving on to 16. Which of these have the highest vapor pressure? So we got to remember vapor pressure is when you have a sealed container and you have liquid in that container. Some of that liquid will become a gas naturally. And vapor pressure is the pressure of that gas. So if you have weak intermolecular forces, you're going to have high vapor pressure. That'll be A, molecule with only dispersion forces. All right, 17. The pure vapor pressure of acetone is 0.050. When I mix acetone with water, the vapor pressure dropped to 0.032. What's the mole fraction of acetone in the solution? All right, so this is another colligative property problem. The pressure of the solution is equal to the mole fraction multiplied by the pure pressure. So the pressure in the solution was 0.032. That is equal to the mole fraction when I'm trying to solve, multiplied by my pure pressure, 0.050. So I'm doing 0.032 divided by 0.050. And so the mole fraction is 0.64. That's the answer for 17. All right, now we call to the Van't Hoff factor. Glucose is a non-electrolyte. What's this Van't Hoff factor? Since it doesn't break down, it's 1. MgCl2 is an electrolyte. What's the Van't Hoff? So I put MgCl2 into water. You get 1 Mg and 2 Cl minus. So I made 3 things. So the Van't Hoff factor is 3. You make a graph of natural log of pressure versus 1 over temperature. So I made that graph. The graph is linear with the equation y equals minus 3.529 x plus b. What is delta H vap? So our slope equals negative 3.529. Remember, our equation was negative slope equals delta H divided by R. R equals 8.314 joules per mole Kelvin. So I can actually do this a different way. I can say negative slope times R equals delta H. Right, so the negative slope, so slope is a negative already. So what negative slope means, if you're still having confusions what negative slope, it's just saying do minus 1 times slope. That equals negative slope. So since slope is negative, negative slope is positive 3.529. Multiply that by 8.314. That equals delta H vaporization. And that should be 29.34. All right, so that's 20. Now comes our short answer questions. So here we are doing freezing point and boiling point changes. So our equations for boiling point, delta TB equals I times molality times KB. And we have the same thing for freezing point, except we use Kf. So first off, the Van't Hoff factor. When you have NaCl, breaks down to Na plus and Cl minus. I equals 2. Molality equals moles of solute divided by kilograms of solvent. So your moles of solute is 1.25. Now our solvent. So we have 2 liters of water. So our solvents. We have 2 liters. So I want to convert that to a weight. And our density tells us that. Our density says for every 1 gram, that is 1 milliliter of water. So I want my solvent to actually be in milliliters. For every 1 liter, there's 1,000 milliliters. Now I can use my density to convert to a weight. For every 1 milliliter of water I have, that's 1 gram. And now I want to be in kilograms. For every 1,000 grams I have, that's 1 kilogram. And you see, we have 1,000 at the top and 1,000 at the bottom. They actually cancel out. So your weight is 2. So your molality, let's do this. I was 2. Your molality is 1.25 divided by 2 is 0.625 multiplied by your Kb, 0.512. So your change in boiling point was 0.64, but I want the actual boiling point. So you have to add that to your normal boiling point. So that's going to be 100 plus 0.64. My boiling point's 100.64 Celsius. Now, freezing point's the same calculation, but you just have a different constant. You have a KF. So it's just the same numbers. So I is 2. Molality is 0.64. KF is 1.86. 1.86 times 0.64 times 2. Delta TF is 2.38, but I want the actual freezing point. So what you do is you take your normal and you subtract it from your TF. So my freezing point is negative 2.38. All right, 22. Why does it take more energy to change a molecule from liquid gas than to solid liquid? All right, so when you're going from a solid to a liquid, you are breaking few intermolecular forces from a liquid to gas. You're breaking all intermolecular forces. Takes energy to break a bond. Therefore, more energy needed for more to break more bonds. More bonds. Right, that's 22. 23. What's the heat of solution given lattice energy and heat and hydration? So delta H solution equals delta H hydration minus delta H lattice energy. So minus 820 minus a negative 750, which means you're adding 750 instead. That's what the double negative sign means. So minus 820 plus 750 is negative 70 kilojoules per mole. And if your heat's negative, that means you're releasing heat. That's an exothermic process. All right, 24. Molality question. I'm trying to dissolve 15 grams of naphthalene into 1.25 liters of benzene. So already, this is my solute. This is my solvent. First is molarity. Molarity is mole solute divided by liter solvent. I'm given grams of solute, so I need to convert. 15 grams of naphthalene. Our molecular weight is 128.17 grams for every 1 mole. The moles of naphthalene I have, let me get my calculator back out. 15 divided by 128.17 is 0.117 moles. So I'm going to take that and divide by liters of my solvent. So divided by 1.25. My molarity then is 0.0936. How about molality? So molality is moles of solute divided by kilograms of solvent. So we already did the moles, is 0.117 divided by the weight of my solvent. And we already did a problem like this with water, but 1.25 liters of benzene. The density of benzene is 0.876, so I need to be in milliliters for every 1 liter. That's 1,000 milliliters. 1 milliliter is 0.876 grams. There's 1,000 grams and 1 kilogram. Again, just like water, the thousands cancel out. So it's just 1.25 times 0.876. So the weight of this solvent is 1.095. So my molality is 0.107 molal. So that's A and B. Let's go down to C. What is the percent by mass? So percent by mass is mass solute divided by mass solute plus mass solvent. And we're going to multiply that by 100%. So I have 15 grams of naphthalene. And that's going to be 15 plus, not have to do benzene again because I just deleted it. So 1.25 liters. For every 1 liter, that's 1,000 milliliters. For every 1 milliliter I have, that's 0.876 grams. Liters also have canceled out. So 1.25 times 0.876 times 1,000. So I have 1,095 grams. Do this division times 100. So 15 divided by 110. So the percentage is 0.901%. So that's the answer to C. Lastly, the heating curve problem I promised everybody. Yeah, so how much energy does it take to convert 150 gram of liquid benzene at 30 C to gaseous benzene at 120 C? The following might be useful. All right, so let's do our temp versus heat curve. We start at 30 C, and we're going to raise our temperature until we hit the vaporization point, which is 78. So we go till we hit 78. Once we're at 78, we do a phase change, so no temperature change. Then once we're done with our phase change, we're a gas, so we go up to 120. So liquid, here we're going from liquid to gas, and gas. So our two equations are Q equals CS times delta T. This is for changing temperatures. And we also have Q equals delta H times N. This is for phase change. So let's do this piece by piece. We have 3 calculations we have to do. So calculation number 1, our mass is 150 grams. The first part, we're still liquid, so the specific heat of liquid is 2.23 joules per gram centigrade, multiplied by my delta T. My final temperature is 78 minus my initial temperature 30. So 70 minus 30 is 48. 48 times 2.23 times 150. That is 16,056 joules, or 16.056 kilojoules. My second calculation, it's Q equals delta H. So I'm doing vaporization here. Condensation and vaporization are opposite processes. So delta H vap is a positive 25 kilojoules per mole then. So 25 kilojoules per mole. I have to multiply it by how many moles I have. So I have 150 grams of benzene. The molecular weight says for every 78.11 grams, that's 1 mole. So I'm taking 150 divided by 78.11. That's 1.92 moles. 1.92. So 25 times 1.92 equals 48 kilojoules. I'm just going to do that again. 2.5 times 1.92. Oh, 4.8. No, sorry. 25 times 1.92. 48. Yeah, 48 kilojoules. Then for my next, once I'm a gas, I'm going to start heating up again. So I go back to my original equation. My mass is 150. I'm in a gas now, so my heat capacity is 1.72 joules gram Celsius. This was grams. My change in temperature, final minus initial, is 120 minus 78. That's where I started from. 120 minus 78 times 1.72 times 150. That's 10,836 joules, or 10.836 kilojoules. Now I'm going to add everything up. So 16.056 plus 48 plus 10.836. My final energy is 74.892 kilojoules per mole. And that's how you solve the heating curve problem. That's it for test 1. So if you had any questions about that, do let me know. Otherwise, I will see you in the next video.